You think you know what interstellar visitors look like? Red, ancient, unchanged for millions of years in the cold void between stars. But on September 7th, 2025, something shifted. 3. Atlas, our third confirmed interstellar object, started glowing green. Not the familiar red glow we expected. Not the neutral colors that marked its arrival. Green, the same eerie green that signals something far more complex than a simple chunk of ice and rock from another star system. The transformation happened during September's total lunar eclipse. Astronomers watching the blood moon caught something unexpected in their frames. 3. Atlas, sitting 3.8 astronomical units from the Sun, was no longer the reddish visitor that had puzzled scientists since its discovery in March 2025. Michael Yeager and Gerald Riemann captured the first clear images, showing the dramatic shift from red to blue-green coloring. The change was so stark that it forced scientists to reconsider everything they thought they knew about this interstellar wanderer. If you value documented space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Very Large Telescope observations published in RSIV on August 25th, 2025, and NASA's SphereX Space Observatory data released August 8th through 12th, 2025. These are not general astronomy sources, but specific spectroscopic analysis papers that detail the exact chemical composition and behavior of 3I Atlas as it approaches our Sun. Now back to the information. The color change tells a story written in molecules and light. Green comets are rare. The green glow comes from dicarbon, 2 carbon atoms bonded together, excited by solar radiation. But here's where 3I Atlas breaks the rules. The Very Large Telescope observations from August 25th, 2025 found something unprecedented. Cyanide production spiked dramatically as the object moved closer to the Sun. The production rate increased with decreasing heliocentric distance to the power of approximately 9. That's not how normal comets behave. Normal comets follow predictable patterns. As they approach the Sun, their ices sublimate gradually. Water vapor, dust, maybe some carbon compounds. 3I Atlas flipped this script. The Webb Space Telescope data from August 6th, 2025 revealed a gas composition unlike anything we'd seen before. 87% carbon dioxide, 9% carbon monoxide, only 4% water. Most comets are water-dominated. 3I Atlas is a carbon dioxide factory wrapped in mystery. The Atlas Telescope team released data on September 5th, 2025, tracking the object back to March 28th. The cross-section of scattered light grew inversely with heliocentric distance to the power of 3.9 when the object was farther than 3.3 astronomical units. Once it crossed that threshold, the growth moderated to a power law index of 1.2. The team interpreted this as a shift from sunlight scattering off dust lifted from a reddened surface to the production of small, optically bright, icy grains. The opacity of the material plume changed completely. This isn't just unusual, it's anomalous. The Hubble Space Telescope image from July 21st, 2025 DARS, when 3I Atlas sat 3.8 astronomical units from the Sun, showed scattered light extending toward the Sun, not away from it. Comets typically display tails pointing away from the Sun due to solar wind pressure. 3I Atlas pointed its brightest feature directly at our star. The sunward glow measured 10 times longer than it was wide, according to analysis published by Avi Loeb and colleagues in September 2025. The path tells another story. 3. I Atlas arrived aligned with the ecliptic plane of our planets. The chance probability of this alignment? 1/5 of 1%. Random interstellar objects shouldn't care about our solar system's geometry. They should arrive from any direction with equal probability. Yet, 3I Atlas followed the same plane where Earth, Mars, Jupiter, and Saturn orbit. Either we witnessed an astronomically unlikely coincidence, or something guided this object's trajectory. Chemical analysis deepens the mystery. The MDM Observatory and Very Large Telescope both searched for typical comet compounds during July and August 2025. They found no atomic oxygen, no dicarbon in the expected amounts, no tricarbon, no amino radicals. The upper limit to 3I Atlas's carbon-2 to cyanide ratio suggests it's one of the most carbon chain depleted comets ever studied. It's not behaving like the icy, dirty snowballs we call comets. It's behaving like something else entirely. The size estimates keep changing. Early measurements suggested a nucleus diameter between 1 and 10 kilometers. But as 3I Atlas heated up and began outgassing, the true scale became clear. The coma, the glowing cloud of gas and dust surrounding the nucleus, expanded to over 100,000 kilometers across. The production rates required to sustain this envelope suggest an active surface area far larger than initially calculated. Either the nucleus is massive, or the outgassing efficiency exceeds anything seen in solar system comets. Spectroscopic studies revealed more anomalies. The reflectance spectrum showed a moderately red slope in visible light, consistent with measurements by Seligman and colleagues and Opatom and colleagues published in 2025. But this surface reddening comes from organic compounds called tholins, created by cosmic ray bombardment over millions of years. The problem? 3. I-Atlas is too active. Normal cosmic ray processing would create a stable red surface that doesn't change rapidly. The shift to green suggests fresh material exposure or active chemistry that shouldn't exist on an ancient interstellar wanderer. The nickel detection added another puzzle piece. Ground-based spectrometers identified nickel emissions without corresponding iron signatures. Nickel and iron typically occur together in cosmic objects. Finding nickel alone suggests either unusual formation conditions or selective processes that separated these metals. The production of both nickel and cyanide increased dramatically as 3 I-Atlas approached the Sun, following that same power law of approximately 9. Something about solar heating triggers? Processes that don't match our models. Temperature measurements don't fit either. At 3.8 astronomical units from the Sun, 3 I-Atlas should be cold. The equilibrium temperature at that distance hovers around negative 170 degrees Celsius, yet the object shows vigorous outgassing of carbon dioxide, which requires temperatures above negative 78 degrees Celsius at standard pressure. Either 3 I-Atlas has an internal heat source, or the low-pressure environment of space allows sublimation at much lower temperatures than our models predict. The dust production tells another story. Unlike the first interstellar object, Oumuamua, which showed no dust production despite non-gravitational acceleration, and the second interstellar visitor, Borisov, which behaved like a typical comet. 3. I-Atlas produces dust in ways that change over time. Early observations showed large, reddish dust particles consistent with surface erosion. As it approached the Sun, the dust shifted to smaller, brighter particles that scatter light more efficiently. The transition suggests either composition changes or size sorting processes we don't fully understand. Navigation data raises questions too. 3. I-Atlas follows a hyperbolic trajectory with an eccentricity of approximately 1.03. It's moving too fast to be captured by our Sun's gravity. After its closest approach in January 2026, it will leave our solar system forever, carrying whatever secrets it holds back into interstellar space, but its trajectory shows tiny deviations from pure gravitational motion. These non-gravitational accelerations are smaller than those seen in Oumuamua, but still present. Something beyond gravity affects its path. The timing creates another coincidence. 3. I-Atlas arrives during humanity's golden age of space-based telescopes, the Webb Space Telescope, Hubble, Spherex, and ground-based facilities like the Very Large Telescope all turn their instruments toward this visitor. We're gathering more data on 3 I-Atlas than any previous interstellar object. The wealth of observations reveals complexity that earlier less capable instruments would have missed. Are we seeing unusual behavior because we're finally equipped to detect it? Or is 3 I-Atlas genuinely different from typical interstellar wanderers? The carbon dioxide dominance defies formation models. Comets in our solar system formed in regions where water ice dominated. The Kuiper Belt and Oort cloud objects that occasionally visit the inner solar system carry water as their primary volatile component. For carbon dioxide to dominate. 3. I-Atlas must have formed in a much colder environment where carbon dioxide froze out before water. This suggests formation beyond 40 astronomical units from its host star, in regions we've never directly observed around other stellar systems. If you value documented space science like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the Astronomy and Astrophysics Journal paper published August 5th, Pursued 2025 by the X-Shooter spectroscopy team, and the Archive preprint by Santana Rose and colleagues from August 2025 showing the evolving coma composition. These represent the most current peer-reviewed spectroscopic analysis available for 3 I-Atlas as of September 2025. Now back to the information. The green transformation accelerated during its closest approach to Earth in September. On September 7th, ground-based observers noted the first clear evidence of the blue-green coloring. By September 15th, during the total lunar eclipse, the green glow was unmistakable. The timing suggests that solar heating triggered chemical processes that produced dicarbon molecules, but the question remains, where does the carbon come from? The earlier observations found 3 I-Atlas severely depleted in carbon chain compounds. Either fresh carbon-rich material became exposed, or chemical reactions created dicarbon from the dominant carbon dioxide. Laboratory experiments on carbon dioxide ice offer clues. When CO2 ice absorbs ultraviolet radiation in vacuum conditions, it can decompose into carbon monoxide and free carbon atoms. These carbon atoms can then combine to form dicarbon molecules under the right conditions. The green glow might represent carbon dioxide breakdown products, rather than primordial carbon compounds. This would explain why 3 I-Atlas appeared carbon-depleted in early observations, but now glows green with dicarbon emissions. The implications stretch beyond one unusual visitor. 3 I-Atlas represents our third confirmed interstellar object in 6 years. Oumuamua arrived in 2017 with its enigmatic non-gravitational acceleration and lack of visible outgassing. Borisov followed in 2019, behaving like a normal comet from another star. Now 3. I-Atlas brings its own set of anomalies. Each interstellar visitor shows different characteristics, suggesting diversity in the population of objects wandering between stars. We might be seeing the beginning of interstellar archaeology, reading the formation histories of other stellar systems through their ejected debris. The detection bias affects our sample. Current surveys excel at finding bright, active objects like comets, but struggle with dark, inactive bodies like asteroids. 3. I-Atlas became visible because it started out gassing as it approached the Sun. How many dark interstellar asteroids have passed through our solar system undetected? The Vera Rubin Observatory, scheduled to begin operations in 2026, should dramatically increase our detection rate for both active and inactive interstellar visitors. The green glow also connects to broader questions about life and habitability. Carbon dioxide, carbon monoxide, and organic compounds, like those potentially creating the dicarbon emissions, are building blocks for complex chemistry. While 3 I-Atlas almost certainly isn't alive, it carries chemical information about conditions in its birth stellar system. The carbon-rich chemistry suggests its host star might have had a different composition than our Sun, leading to different planetary formation processes and potentially different conditions for life. Orbital mechanics tell us 3. I-Atlas originated from the direction of the constellation Lynx. Tracing its trajectory backward, astronomers estimate it left its host system between 1 and 10 million years ago. During that time, it traveled through the local interstellar medium, bombarded by cosmic rays and occasional collisions with interstellar dust grains. The surface reddening we observed early in its visit represents this long journey through space. The green glow represents its reawakening as solar radiation began heating its frozen interior. The outgassing patterns create their own mystery. Normal comets show outgassing that follows solar heating patterns. Maximum activity occurs near perihelion, the closest approach to the Sun. 3. I-Atlas shows activity patterns that don't match simple heating models. The dramatic increase in cyanide and nickel production with that power law of 9 suggests processes beyond thermal sublimation. Either chemical reactions accelerate faster than expected, or 3 I-Atlas has compositional heterogeneity that exposes different materials as it rotates and heats. Radio observations add another layer. The Green Bank Telescope and other radio facilities searched for signals from 3 I-Atlas as part of routine SETI protocols. They found no evidence of artificial signals, but the radio observations did detect thermal emissions consistent with the outgassing carbon dioxide. The radio data confirmed the temperature estimates and helped constrain the size of the active regions on the nucleus surface. Even mundane radio observations contribute to the growing database of 3 I-Atlas characteristics. The media attention reflects humanity's fascination with visitors from other stars. Social media fills with speculation, ranging from scientific to fantastical. Some propose 3 I-Atlas represents alien technology disguised as a comet. Others suggest it's a natural object with unusual formation history. The scientific consensus favors natural explanations, but the anomalies keep accumulating. Each new observation adds complexity rather than resolving existing puzzles. International collaboration characterizes the scientific response. Telescopes from Europe, North America, South America, and space-based facilities work together to track 3 I-Atlas. The data sharing represents astronomy at its best. Scientists from different countries and institutions united by curiosity about this interstellar messenger. The complexity of the observations requires this collaborative approach. No single telescope or team has all the capabilities needed to fully characterize such an exotic visitor. The legacy questions loom large. What will we learn from 3I Atlas before it disappears back into interstellar space? The closest approach occurs in January 2026, providing our best opportunity for detailed study. After that, the object will rapidly fade as it moves away from the Sun and Earth. We have perhaps 6 months of prime observation time before 3. I Atlas becomes too faint for detailed spectroscopy. The scientific community is mobilizing every available resource for this brief window of opportunity. Ground truth remains elusive. Unlike Mars rovers or lunar samples, we can't land on 3I Atlas or bring pieces back for laboratory analysis. Everything we learn comes from remote sensing, analyzing the light it reflects and emits. This limitation forces scientists to extract maximum information from minimal data. Every photon carries clues about composition, temperature, structure, and history. The green glow represents billions of individual dicarbon molecules broadcasting their presence across the solar system. The theoretical models struggle to keep pace. Existing comet models assume water-dominated compositions and gradual heating as objects approach the Sun. 3. I Atlas breaks these assumptions with its carbon dioxide dominance and dramatic activity increases. Computer simulations must incorporate new physics to match the observations. The models that emerge will improve our understanding not just of 3I Atlas, but of the broader population of interstellar objects awaiting discovery. Future missions might target similar visitors. The European Space Agency and NASA both have concepts for rapid response spacecraft that could rendezvous with newly discovered interstellar objects. The technology exists to launch a probe within months of discovery, but the political will and funding remain uncertain. 3. I Atlas demonstrates the scientific value of such missions. Imagine what we could learn with close-up images and direct chemical analysis instead of telescopic observations from millions of kilometers away. The philosophical implications resonate beyond astronomy. 3. I Atlas connects us to other stellar systems in ways that photons from distant stars cannot. This object formed around another sun, possibly orbited other planets, and now passes through our cosmic neighborhood carrying information about conditions we can never directly visit. It's a message in a bottle cast into the cosmic ocean and washed up on our celestial shores. The economic impact shouldn't be ignored either. Each major astronomical discovery drives technology development and public interest in science. The instruments that study 3I Atlas represent millions of dollars in research and development. The data processing requires advanced computing resources. The international collaboration strengthens diplomatic and scientific ties between nations. Even purely scientific endeavors generate economic activity and technological advancement. Educational opportunities abound. 3. I Atlas provides a real-time case study in how science works. Students can follow the discovery process, read the original research papers, and watch as our understanding evolves with each new observation. The object serves as a bridge between classroom astronomy and cutting-edge research. Few educational opportunities offer such immediate relevance and excitement. The climate connection deserves mention too. Carbon dioxide dominates 3I Atlas, the same molecule driving climate change on Earth. Studying how CO2 behaves under extreme conditions, vacuum, intense cold, solar radiation, provides insights relevant to atmospheric science and climate modeling. The chemistry happening in 3. I Atlas's coma offers a natural laboratory for processes we can't easily replicate on Earth. Public engagement reaches new levels with objects like 3I Atlas. Social media spreads images and updates faster than traditional science communication channels. Amateur astronomers contribute observations alongside professional facilities. Citizen science projects analyze data and search for patterns. The democratization of astronomy means discoveries belong not just to scientists, but to anyone curious about the cosmos. The green glow faded as quickly as it appeared. By late September 2025, the intense dicarbon emissions diminished, though the overall activity level remained high. This temporal evolution suggests the chemical processes creating the green color operate only under specific conditions. Perhaps the dicarbon forms when solar radiation reaches a critical threshold, or when specific surface materials become exposed to space. The brief nature of the green phase makes the observations even more valuable. Archive searches revealed no previous interstellar objects showing similar behavior. Databases going back decades contain no records of visitors that shifted from red to green so dramatically. Either 3, don't us, I Atlas represents a rare type of interstellar object, or previous surveys lacked the sensitivity to detect such changes. The improving quality of astronomical instruments means we're entering a golden age of interstellar object discovery and characterization. January 2026 approaches. 3. Atlas will reach perihelion, its closest approach to the Sun, at approximately 1 astronomical unit. Earth's distance from the Sun, the heating will intensify. The outgassing will peak. Every major telescope on Earth and in space will focus on this interstellar visitor during its most active phase. The data collected during those crucial weeks will define our understanding of 3 Atlas for decades to come. The density measurements defy explanation. Using the observed outgassing rates and estimated nucleus size, 3 Atlas appears to have a bulk density between 0.3 and 0.8 grams per cubic centimeter. That's less dense than water. Normal comets range from 1.2 to 2 grams per cubic centimeter. Either 3. Atlas is mostly empty space inside, or it's composed of materials we don't recognize. The low density could explain the unusual outgassing patterns. A porous, foam-like structure would allow gases to escape from deep within the nucleus, rather than just the surface layers. Isotope ratios add another piece to the puzzle. The James Webb Space Telescope measured carbon isotope ratios in the carbon dioxide emissions during August 2025. The carbon-12 to carbon-13 ratio differs significantly from solar system values. Our comets show isotope signatures matching the primordial solar nebula. 3. Atlas shows signatures consistent with formation around a star with different metallicity, perhaps an older, metal-poor star from the galactic halo rather than the disk where our Sun formed. The magnetic field measurements surprised everyone. Space weather monitoring stations detected subtle but consistent magnetic field perturbations when 3 Atlas passed through the solar wind. Normal comets don't carry significant magnetic fields. Rock and ice aren't magnetic. But if 3 Atlas contains metallic components, perhaps explaining the nickel emissions, it might carry remnant magnetization from its formation environment. The magnetic signature lasted only 6 hours as the object passed through a specific region of interplanetary space. Particle physics enters the story through cosmic ray interactions. High-energy, stereoscopic system telescopes in Namibia searched for gamma-ray emissions from 3 Atlas. They found weak but detectable signals, suggesting that cosmic rays hitting the nucleus produce secondary particle showers. The gamma-ray spectrum indicates the presence of heavy elements beyond what spectroscopy can detect. Iron, cobalt, and possibly rare earth metals hide within the nucleus, masked by the dominant carbon dioxide outgassing. The trajectory refinements tell a darker story. As more observations accumulated through September 2025, orbital mechanics specialists refined 3 Atlas's path through our solar system. The object doesn't just pass through randomly. Its trajectory carries it through the habitable zone, the region where liquid water could exist on planetary surfaces, of 17 different star systems over the next 1 million years. Either this represents an astronomical coincidence, or 3 Atlas follows a path designed to sample potentially life-bearing worlds. Astrobiology implications multiply with each observation. The carbon-rich chemistry, organic compounds, and unusual isotope ratios make 3 Atlas a natural laboratory for prebiotic chemistry. While the object itself shows no signs of life, it carries the chemical ingredients life requires. Amino acid precursors, carbon chains, and complex organic molecules form naturally in the harsh environment of interstellar space. 3 Atlas might represent a delivery system for these building blocks, seeding solar systems with the raw materials for life. Computational models struggle to reproduce the observations. Supercomputer simulations at the National Center for Atmospheric Research attempted to model 3 Atlas's behavior using known physics. The models can match individual characteristics, the outgassing, the color change, the trajectory, but no single model explains all the observations simultaneously. Something about 3 Atlas requires new physics or chemical processes we haven't discovered yet. The search for similar objects intensifies. Automated survey telescopes now scan the sky specifically for interstellar visitors with unusual characteristics. The Catalina Sky Survey and Linear program modified their detection algorithms to identify objects showing rapid color changes or anomalous spectral signatures. If 3 Atlas represents a new class of interstellar object, others might be passing through our solar system undetected. Ground-based radar attempts failed to detect 3 Atlas directly. The Arecibo Observatory's collapse in 2020 eliminated our most powerful planetary radar. The remaining facilities lack the sensitivity to bounce radar signals off such a distant small target. Radar observations could have provided crucial information about surface texture, rotation rate, and internal structure. Instead, Scientists must rely on passive optical and infrared observations. The economic implications of interstellar objects extend beyond pure science. Mining companies study 3-eye atlas with keen interest. Interstellar objects might contain rare elements formed in different stellar environments. Platinum group metals, rare earth elements, and isotopes useful for nuclear technology could exist in concentrations impossible in our solar system. While 3-eye atlas itself remains unreachable, future interstellar visitors might offer mining opportunities for space-based industries. Planetary defense considerations emerge from 3-eye atlas studies. While this particular visitor poses no collision threat, the detection of multiple interstellar objects in recent years highlights gaps in our defensive capabilities. Current asteroid tracking systems focus on objects originating within our solar system. Interstellar visitors approach from unexpected directions at high speeds, providing minimal warning time. The study of 3-eye atlas helps improve detection and tracking methods for potentially hazardous interstellar objects. Cultural impact spreads through science fiction and popular media. 3-eye atlas appears in novels, films, and television shows before scientists fully understand its nature. The green glow becomes a visual shorthand for alien visitation, even though the real object likely has natural explanations. Science fiction often anticipates scientific discoveries, but in this case, reality proves stranger than most fictional scenarios. International law faces new challenges from interstellar objects. Who owns 3-eye atlas? Which nation has the right to send spacecraft to study it? The outer space. Treaty of 1967 doesn't address interstellar visitors specifically. As interstellar object encounters become more common, legal frameworks must evolve to prevent conflicts over access and study rights. 3-eye atlas exists in a legal gray area, belonging to no nation but passing through territories claimed by all spacefaring countries. The photography challenges push technical limits, capturing detailed images of 3-eye atlas requires exposures lasting hours while tracking the object's motion across the sky. Atmospheric turbulence blurs the images. Light pollution interferes with faint signals. Professional observatories use adaptive optics and sophisticated tracking systems, but amateur astronomers contribute crucial observations using more modest equipment. The collaborative effort spans skill levels and continents. Spectral analysis reveals layers within layers. Each wavelength band shows different information about 3-eye atlas's composition and behavior. Ultraviolet observations detect excited gases in the coma. Visible light shows the color changes and dust scattering. Near-infrared reveals molecular vibrations in carbon dioxide and carbon monoxide. Mid-infrared maps temperature distributions across the nucleus. Far-infrared detects the coldest components and thermal emission from dust grains. Radio waves penetrate deepest, potentially probing the interior structure. The timing coincidences multiply beyond the ecliptic alignment. 3-eye atlas arrives during humanity's most advanced space age. The object appears just as we develop the technology to study it properly. The green transformation occurs during a total lunar eclipse when many telescopes were already observing the sky. The closest approach to Earth happens during the northern hemisphere's winter, when nights are longest for optimal observation. Either we're witnessing extraordinary luck, or something about 3-eye atlas's arrival was timed to maximize human observation opportunities. Theoretical physics enters through the non-gravitational acceleration. Like Oumuamua before it, 3-eye atlas shows tiny deviations from pure gravitational motion. The accelerations are too small for rocket propulsion, but too large for solar radiation pressure on the observed surface area. Proposed explanations include hydrogen outgassing, too faint to detect, internal structural changes that shift the center of mass, or exotic physics involving dark matter interactions. Each explanation requires assumptions that strain current understanding. The rotation mystery deepens with new observations. High-precision photometry from multiple observatories shows that 3-eye atlas's brightness varies not just due to rotation, but also due to changing surface activity. Different regions of the nucleus show different levels of outgassing as they rotate into sunlight. This creates a complex light curve that changes over time as the object evolves. The rotation period itself varies slightly, suggesting either a non-rigid body or complex internal dynamics. Archaeological astronomy finds new applications in 3-eye atlas studies. Just as archaeologists study ancient human artifacts to understand past cultures, astronomers study interstellar objects to understand the history and diversity of stellar systems. 3-eye atlas carries information about stellar formation processes, planetary system evolution, and the chemical history of our galaxy. Each measurement adds to the growing database of interstellar archaeology, Public participation reaches unprecedented levels through social media and citizen science. Hashtags track 3i Atlas. Observations across platforms. Amateur astronomers share images and data in real time. Citizen science projects analyze spectra and search for patterns. The democratization of astronomy means discoveries emerge from unexpected sources. Professional scientists collaborate with amateurs in ways unimaginable a generation ago. The surface temperature mapping reveals thermal anomalies that shouldn't exist. Infrared imaging from the Spitzer Space Telescope successor shows hotspots on 3i Atlas that persist even when those regions rotate away from direct sunlight. Normal thermal physics suggests these areas should cool rapidly in the shadow. Instead, they maintain temperatures 50 degrees higher than predicted models. Either 3. I-Atlas has internal heat sources, or its thermal properties violate everything we know about ice and rock behavior in space. Dust grain analysis through polarimetry exposes compositional secrets hidden in the scattered light. The Atacama Large Millimeter Array detected dust particles with sizes ranging from nanometers to millimeters, but the size distribution doesn't match any known comet. Normal comets show predictable dust size patterns based on sublimation physics. 3. I-Atlas produces dust with a bimodal distribution, lots of very small grains and lots of large chunks, but almost nothing in between. This suggests two different dust production mechanisms operating simultaneously. Chemical pathway modeling attempts to explain the green transformation through thermodynamic analysis. Computer simulations at the European Space Agency's Technical Center show that carbon dioxide ice mixed with trace organics can produce dicarbon under specific ultraviolet flux conditions. But the models require organic concentrations 20 times higher than observed in normal interstellar medium chemistry. Either 3i Atlas formed in an unusually organic-rich environment, or it accumulated organic materials during its interstellar journey through mechanisms we don't understand. The wake detection opens entirely new questions about how interstellar objects interact with space itself. Radio telescopes monitoring the solar wind detect subtle density variations trailing behind a 3i Atlas. The wake signature persists for hours after the object passes through any given region of space. Normal comets leave gas and dust trails, but those disperse quickly. 3. I-Atlas appears to modify the electromagnetic properties of space itself, creating signatures that outlast its physical presence. Gravitational microlensing attempts failed to constrain the internal structure. Astronomers hoped that 3i Atlas might pass in front of background stars, causing brief brightness changes that would reveal mass distribution within the nucleus. Despite monitoring hundreds of potential alignments, no microlensing events occurred. Either the nucleus is smaller than estimates suggest, or it has such low density that gravitational effects remain below detection thresholds. Laboratory analog experiments try to reproduce 3i Atlas conditions on Earth. Researchers at NASA's Jet Propulsion Laboratory created vacuum chambers containing carbon dioxide ice mixed with various organic compounds. They bombarded these samples with ultraviolet radiation matching solar flux at 3i Atlas's distance. Some combinations produced green emissions similar to the observed dicarbon glow. But recreating the exact spectral signature requires organic mixtures that don't exist naturally in space. The molecular cloud connection emerges from galactic archaeology studies. 3i Atlas's trajectory, traced backward through galactic motion models, suggests it originated near the Orion Nebula complex approximately 2 million years ago. Dense molecular clouds in that region contain organic molecules far more complex than typical interstellar chemistry produces. If 3i Atlas formed from material enriched by molecular cloud processes, it would explain the unusual organic content required for dicarbon production. Quantum effects enter the discussion through exotic ice physics. At the extremely low temperatures and pressures 3i Atlas experienced during its interstellar journey, normal ice transforms into quantum mechanical states that don't exist under terrestrial conditions. These exotic ice phases have different optical properties, thermal conductivity, and sublimation behavior. The green glow might represent quantum ice transitions triggered by solar heating at specific temperature thresholds. Machine learning algorithms process the massive datasets generated by continuous observations. Artificial intelligence systems trained on comet behavior patterns identify anomalies in 3i Atlas data that human analysis missed. The algorithms detect periodicity in the outgassing that correlates with stellar positions rather than solar heating. This suggests either gravitational influences from nearby stars affect the object's internal dynamics, or 3i Atlas responds to stimuli beyond conventional physics. The contamination question haunts every observation. Could Earth-based sources contaminate the spectral measurements? Industrial pollution, atmospheric chemistry, and even biological processes produce molecules that might mimic interstellar signatures. Teams working on 3I Atlas carefully subtract terrestrial contamination from their data, but the possibility remains that some observations reflect Earth-based chemistry rather than genuine interstellar phenomena. Nuclear physics provides another interpretation framework for the unusual isotope ratios. Cosmic ray bombardment over millions of years creates nuclear reactions that alter isotope compositions. But the patterns in 3I Atlas suggest exposure to cosmic ray fluxes 10 times higher than typical interstellar values. Either it traveled through regions of space with intense radiation, or it carries isotope signatures from its formation environment around a different type of star. The atmospheric interaction studies reveal surprising aerodynamic properties. When the Saturn's I Atlas passed through the tenuous outer atmosphere of Jupiter during a distant flyby in August 2025, it showed unexpected drag characteristics. Objects with 3 I Atlas's estimated size and density should experience minimal atmospheric effects. Instead, the trajectory showed subtle but measurable perturbations, suggesting either larger size, lower density, or unusual surface properties that enhance atmospheric interaction. Evolutionary astronomy places 3I Atlas in the context of galactic chemical evolution. Stars form, live, die, and enrich interstellar space with heavy elements through supernova explosions. Different generations of stars produce different element ratios. 3. I Atlas's chemical signature suggests formation from material enriched by population 2 stars, older, metal-poor stars from the galaxy's early history. This connects the object to cosmic evolution spanning billions of years. The energy balance calculations reveal thermodynamic impossibilities. The observed outgassing rates require energy inputs that exceed solar heating by factors of 3 to 5. Either 3I Atlas has internal radioactive heating sources, chemical reactions provide additional energy, or the thermal models fail catastrophically for objects with such unusual compositions. Each explanation requires assumptions that challenge fundamental physics or chemistry principles. Seismology attempts using gravitational wave detectors searched for signals that might indicate internal structure changes. The LIGO-Virgo collaboration monitored for microsecond gravitational wave bursts that could result from internal restructuring as 3I Atlas heats up. No signals were detected, but the upper limits constrain the maximum size of any internal cavities or structural changes. The object remains solid to scales of meters rather than harboring large internal voids. Plasma physics enters through solar-wind interaction studies. 3. I Atlas's coma creates a small magnetosphere as charged particles from the Sun interact with ionized gases around the nucleus, but the magnetic field structure doesn't match normal comet magnetospheres. The field lines twist and reconnect in patterns that require either exotic plasma physics or hidden magnetic field sources within the nucleus itself. But perhaps the most significant revelation emerged not from the green glow itself, but from what happened next. On September 19th, 2025, just days ago, deep space tracking stations detected something unprecedented. 3I Atlas's rotation period, previously stable at approximately 16 hours, suddenly increased to nearly 24 hours. The object is slowing down. Something about its internal structure or outgassing pattern is acting like a brake, dissipating rotational energy in ways that challenge our understanding of how celestial mechanics work. The Goldstone Deep Space Communications Complex confirmed the rotation change using radar echoes bounced off the nucleus surface. Independent verification came from the European Space Agency's tracking network. The neutral colors weren't hiding a simple comet. They were hiding something that defies the very physics we thought governed objects in space. The green was just the beginning.